calculus, there's a class called differential equations that is awesome. And this is like a little tiny little snippet of what you talk about in differential equations. Okay, so I printed these out for you, so really fast, right? But we say, this is kind of a new concept here, but I feel like it should make sense to you, that differentiable curves, so curves that are smooth, that are differentiable, no sharp points, no cusps, are locally linear, which means if I had a parabola here, and I just kept zooming in on this little section, like on my calculator, and I hit zoom and zoom and zoom and zoom, do you agree that eventually if I zoomed in enough, that little section would just look like a straight line? Do you agree with that idea? You can try it. If we had lots more time, I'd have you get your calculators out and try it, but I don't want to waste our precious minutes. That it's locally linear. So what we say is that we can use tangent lines to approximate the value of a curve. So let's say I wanted to know the value right here, and I didn't have the equation of the curve, or maybe it was a really complicated equation. If I just found the tangent line's a straight line, it would get me pretty close to what the actual value is. All right, so that's what we mean by linear approximation. We're going to use a linear line to approximate the value of a nonlinear line. All right, so I kind of not a big fan of the way the book writes this, but this is what they say. They say if x is a differentiable function at some point, good thing Sean isn't here, x equals a, meltdown, then the equation for the tangent line is this. Let me just show you where this comes from. When we write an equation for a tangent line, what do we always need? A slope and a point. Yes? So if my point, let's say my point was a f of a, yes? Do you agree that's my point? My slope would be the same as saying the derivative at a. Do you agree with that statement? And we use point-slope form, yes? So could I say, when I write my equation, point-slope form, we do y minus y1 equals m times x minus x1? What if I just plug these values in instead of y1 and m and x1? You should get a very similar statement than what they give you. The point that I'm trying to make is you don't have to feel like you have to memorize this equation. It's just point-slope form moved around a little bit. Because y1 would be f of a. Do you agree with me on that? So I get y minus f of a. My slope is f prime of a and x minus a. How do they go from this to this? They just add that over, right? And so I'm not gonna use this really much. You're welcome to memorize it and go straight from there. Because I feel like this is what we do all the time. We make tangent lines. The only difference is we're going to solve for y, so we're going to add that over to get our answer. All right, so I just want you to be aware that this is just point-slope form. They've just plugged in the point, which is a. They've plugged in the derivative, and then you leave x in that problem. Okay, so it's just a linear equation for a tangent line. The book talks about this L of x and f of x, and it's in the directions of your homework, which is why I give you this, because if not, when you get to your homework, you're going to freak out and be like, I don't know what this means. But basically, we can say that the function approximately equals our tangent line, and we can estimate things that we don't really need to estimate anymore. But back in the olden days, it was really cool that people could estimate square roots, and they could estimate ln's when they didn't have just a handy-dandy calculator with them, that you could approximate these. And I think I'm supposed to draw a picture here that I already kind of drew. I think I drew this already, but we'll say this. This is A. This is my tangent line. And so if I want to know the value of the function at A, that tangent line is going to be pretty darn close to that. So let's look at the ways we're using the book. On your AP exam, I'll guarantee there's going to be a question that says use a linear approximation to find this value. Not worded as weirdly as your homework, but it's just a tangent line. what your book says today. Problems like this. It says use the linearization of this function, and they give you a value for a, so at 0, to approximate the value of the square root of 1.02 without a calculator, and then use a calculator to check your answer. So it's kind of just a way to show you that linearization gets you really close to the answer that your calculator gives you. And think back, even when I was in school, I'm not that old, but even when I was in school, like, I didn't have a calculator until I was in high school. So, like, in junior high school, like, everything we did was without a calculator. And then, like, my parents, I mean, you can ask your parents even, probably didn't have a calculator. And if you go to your grandparents, they used a slide rule to do things like logs and ln's and square roots. They used a slide rule to calculate it all. That's kind of very weird concept. But, all right. So, here we go. A equals 0. Yes, we need that. That's our x value. Can we find our y value to go with that? F of 0 would be, when we plug 0 in here, do you agree that I just get the square root? I'll show my work here so you can see where it's coming from. 1 plus 0, which is just 1. No, because that's the function they give us. The only time you do plus or minus is when you take the square root of both sides of an equation, if it's not talking about geometry. Okay?
So A and X are the same thing.
A is the value. A is the value that you're trying to find on your curve. Okay? X is the X that always stays in your equation. Think about when we write a slope form of an equation, we write stuff like this, right? X stays in there. So when we get to our final answer, X is going to stay in our problem for a minute. A is where on the graph we're looking for. Does that make sense? So, like, if I'm looking at this, do you agree that this could also be called an X value, but it's the point that I'm talking about? So that's the whole confusion about A equals X.
Teachers, please excuse the interruption. I need Candace Weddle to please report to the office. Candace Weddle to the office.
If I'm writing a tangent line, I have a point. What else do I need? A slope. So I need f prime of 0, which means this is where you got to do some calculus. Let's go up here. Here was f of x. Can we find the derivative and then plug 0 in? You can't plug 0 in and then find the derivative. That doesn't work. Find the derivative and then plug 0 in. So maybe I should go back here and say let's find f prime of x, which would be 1 plus x to the 1/2 power. So that would be 1/2, 1 plus x to the negative 1/2. And the derivative of the inside of this would just be 1. So you don't have to write that. I mean, you can. So if you clean that up, the 2 is going to go on the bottom. This is going to go on the bottom too. And I'm going to go ahead and plug 0 in there. Do you agree with me on that? Which means my slope is 1/2. I'm okay if you want to use the formula on that other page, the L of x equals. But I'm also want you to think about you're not going to necessarily have that formula memorized by the time we have a test, which is why I like to say we found everything we need here. All we have to do now is find a tangent line and solve it for y. They just call it L of x. So do you agree that if I use my point, which is 0, 1, and I use my slope that's 1/2, I can write my tangent line. Y minus 1 equals 1/2 times x minus 0. And if you add 1 over, I just want you to notice that this is the exact formula on the other page. This is f of a, this is f prime of a, this is x minus a. So it's the exact formula. I don't care which one you use. I don't have that formula memorized. I've never memorized it. And when I first taught AP Calculus, when we got to the AP test, I was like, oh, I don't remember that formula. And then Graham Carr pointed out to me that I didn't need that formula, and I could just use my slope bar. The difference is they call that L of x, which just means that's your linearization. And that would just be 1 plus 1 half x if I worked it out. Yes? That is our linearization. What do they ask us to do? Use the linearization to approximate this value. So I think this is kind of the tricky part of this. What are we going to plug in to our function here to approximate this value? Or basically, what would x have to be? What x would I have to plug in here to get this number out of it? 0.02. So I just want you to see that you're not going to plug in 1.02. You're just going to plug in the difference between what would x have to be to get this. And you'll notice you're always going to plug in little numbers, because if you go really far away, then it's not going to be that accurate anymore. Like, you have to be really close to the point that you're looking at. So we're going to plug in 0.02 and see if we can figure this out without a calculator. How would you do 1/2 times 0.02 without a calculator? You could totally just do the arithmetic there. I always think about changing to a fraction. How do you say 0.02 instead of 0.02? That's the same as saying 200ths. Yes? So that, I tend to go that way. I'm a crazy decimal person, or fraction person, so maybe I'm just a weirdo. But do you agree that those 2's would cancel out, and that would be left with 1/100th? Or that could be written like that. Or we can say that the linearization, which is really just an approximation, gives us an answer that the square root of 1.02 is 1.01. And then you can check on your calculator. The square root of 1.02 on my calculator said 1.00995. Pretty close, right? Pretty good approximation for back in the day when they didn't have a handy-dandy calculator. You guys are always very unimpressed by this because you have calculators that will tell you, but don't leave. Let's see what we can do. I'm so disappointed, kids. Let's try this. Let's try these first 3 problems.